So we just looked at a plan infini, okay? A plan infini, and it had a lot of charges. It contains distribution of charges, of course. So here we're going to use a cylinder as the surface de Gauss. So a cylinder cuts through this plan infini, okay? So which means the only charge that is going to be inside is a charge on this disk. The other charge will be outside. So which makes theorem de Gauss ideal. Then according to theorem de Gauss, we say that the double integral of E dot ds is equal to Qn over epsilon 0. So now we're going to deal with the first part, then we're going to deal with the second part. So just a quick summary of what we've done. Then this we're going to have S1, S2, S3. Then this disk where there are charges, we're going to call it S4. We know that S1 is equal to S2, which is equal to S4, which we're going to call S. Okay. Now, this left-hand side, you're going to decompose it into the three surfaces. Okay. Integral of E on S1 dot plus integral E dot ds2, then plus integral E dot ds3. Okay, then you just check which integrals, which you know that E is in the z direction, E k, okay, up or down. So you know that S1 is up, so E is also in the z, up or down. So E is up, so this is valid. Okay, S2 is also valid, but for S3, if you look at the diagram, this is the direction sideways, it's perpendicular. So this one is going to give us 0. Okay, this is going to give us 0. And then, which means that, and then E and the surface, these surfaces, they are independent of E. Okay, so what you can do here to convert, these are two vectors. To convert them into non-vectors, you just multiply them. Okay, you just multiply them. To convert these into non-vectors, you just multiply them. I'm going to have E ds1 plus E ds2. Then this one is 0. Okay, so E is independent of ds1, so you just take it out of the integral. E ds1 plus E ds2. Okay, now whenever you have this situation, it's just S1. Okay, you're summing up all the small S1s, so it's just S1. So E S1 plus E S2. So now you know that S1 and S2 are equal. Okay, you know that S1 and S2 are equal. So S1 is equal to S2, which is equals to S. So here we're going to have ES plus ES, which is going to be 2ES when you add them. So this will be your right hand side. Okay, oh, left hand side of the theorem de Gauss. Okay, now we're going to look at Q in for the right hand side. You know that the only charge that is enclosed is on a disk. Okay, we have a disk of charges, a uniform distribution of this, and the surface, this surface is also equal to S. Okay, so when you have charge, whenever you have a distribution of charges, think of charge densities. So if you have a surface, you think of surface density. If you have a volume, you think of volume density. If you have a line, for example, a wire, you think of line densities, and they have different Greek symbols to signify for them. Now, this is surface density. So for you just calculate Q. This is the only charge inside. It's as simple as that. This is the charge inside, according to theorem de Gauss. So the charge inside is equal to um, the charge inside is equal to Q in is equal to surface density multiplied by S. Okay, you just multiply by the surface. So sigma S. So on volume plus C. From the equation, our right hand side has got Q in over epsilon 0. Okay, so the left hand side had 2 ES, then the right hand side had Q in, which is sigma S over epsilon 0. Now, don't forget what we're calculating. What are we calculating? We're calculating E, show electrostatic. So E will be equal to this S and this S can cancel. You're going to have sigma over 2 epsilon 0. Now, this is just the magnitude, the E magnitude. So now, for you to calculate E as a vector, E as a vector is going to be equal to um, sigma over 2 epsilon 0. Then in the direction of Z, in vector in the direction of Z to show. Okay. So if, for example, if the point is upwards, this is the plan fini. If the point is upward, this is the origin. Okay. If the point is upward, we know that in this, since it's a composite of Z, if it's upwards, Z is positive, so it will just be positive. But if it's downwards, okay, the unit, if it's downwards, it will be negative, negative 2 over when Z is less than 0. When Z is greater than 0, Z is greater than 0 positive, because E is dependent on the Z axis, in the direction of Z. So if Z is negative, it will also be negative. E will be, if Z is positive, it will also be positive. As simple as that. So now, this is a method of calculating the show electrostatic using the theorem de Gauss of the plan infini, of an infinity plane. Okay, now we're now going to demonstrate using the same formula, but for now we're now going to calculate for the disk. Okay, this is a disk now, and in the introduction I said a plan infini is equivalent to a disk of where the radius approaches infinity. That is where there's radius, you put infinity. Okay, then from the study of planes of symmetry, okay, so this is the disk. We're going to understand elementary part. Okay, this is the disk. Let me try to do some drawing. So this is the coordinate system. So we're going to use the spherical coordinate system for a disk. Okay, then this is the disk here. I'm sure you've seen it. Okay, so now from this disk, okay, we know that if you remember the coordinate system, this is phi. Okay, and the radius here, so this is from, let's say this disk has got the radius of r. Okay, so the radius is r. Okay, then so what we're going to do is we're going to get, follow me nice. In order for you to calculate for a disk, you first calculate the show electrostatic created by a smaller portion of the disk. So I'm going to get, for example, for me, I'm going to get a smaller portion. I'm going to get maybe, no, let me do this. I'm going to get this portion of the disk. Okay, I'm going to cut off this portion, which is like this. Okay, then I'm going to calculate the show electrostatic created by this portion. Since it's a smaller portion, I'm going to call this portion ds. The entire disk, the surface is s, so I'm going to call this ds. Okay, you should follow me nice. So if I cut it off from here, this is a portion. So as a result, because it's an elementary portion, the show electrostatic that I'm going to calculate is also elementary, will be dE. Okay, now for this elementary surface, all you need to know is you need to know the formula for the area. Okay, so to begin with, this is uh, a chip, or we've just portioned out, for example, we've just portioned out the part of this surface. Do I have, Okay, so this is the part that you've chopped out. Okay, so now from your center coordinate system, you know that the angle here is phi, then the radius here, the total radius of the disk is maybe r. Then you're going to use, for example, the radius of this, because you're already using r, you're going to use maybe, because this is a portion, if you see this is a portion of r, then this is 0, maybe this was the entire disk. Okay, and you got this portion, so this will, you call it rho. Okay, this distance here, and then this was nice, this angle was phi. Okay, so from here to here, this will be a change of phi. Okay, so this will be d phi. D phi to mean a smaller portion of our angle. This angle is phi, then this will be d phi. Okay, and then mind you, we're just studying what the show electricity got to be created by a small portion. Then we're just, when we find the answer, we're just going to integrate it in order for us to find for the total now. Okay, we're just going to apply integration. It's going to apply everyone. Then for you, in order for you to find this is the portion that we've chopped out. In order for you to find the area of this portion, let's call this portion of the radius as rho. Okay, then what will be the length here? The length here will be arc length, the length of this side. So how do you find arc length? Arc length will just multiply angle multiplied by this side, okay, which is rho. So arc length will be rho d phi. Okay, now this can be seen as a rectangle. How do you define area of rectangle? A multiplied by b. So boys, ladies and gentlemen, so for you to find the area ds, you're going to multiply. Yeah, so this is a smaller portion of the radius. So we're going to call this entire radius as rho. Okay. Then if you get a smaller portion of it to be d rho. So I made a mistake. D rho here. Okay. Then for you to find the arc length, since we're going to call this, okay, this portion from here to here as rho. Okay. From here to here as rho. So for you to find the arc length is d phi multiplied by rho. Okay, so all this information is to help you know that the formula for ds in as a cylindrical coordinate system is rho d rho. When you multiply this, multiply by this. Okay, so you're going to have rho d rho, then d phi, as simple as that. So in short, in simpler terms, in case you find this confusing, if you want to find the elementary ds will just be equal to, you say the smaller portion, this is the surface, then the small portion you call it d rho, then this is d phi, then this is the arc length rho. Okay, rho phi, the angle phi is always associated with the arc length, so you just multiply. We say d rho multiplied by d phi, but since d phi is always associated with the radius rho, so you put rho here. So therefore, the area of the elementary area doesn't change. So the area is rho d rho d phi. Okay, that's how you find the elementary area from of this portion, the elementary. So what looking at an elementary surface, so everything will be elementary. So even the show electrostatic. So now going to consider the show electrostatic created by this point, this charge. Then let's say we know that the show electrostatic is in the z direction, so maybe it can be here. Maybe let's say the point M. Okay, so what is the show electrostatic created on the point M? Okay, so now, so you're going to attach this to M, because the point M can be anywhere on the axis, because that's what E is dependent on. Okay, so now you're going to apply the actual formula now for E. Okay, what is E? Show electrostatic by definition. By definition, we said that E is equal to, let's say, where the charge is, let's say this is point P and this is M. So the show electrostatic that will be created on M will be equal to, we said we define this to be the charge. Now the charge will be elemental. Okay, the charge will be elemental on this surface. Don't forget. Okay, so the charge will be dq will also be elemental, dq over 4 pi epsilon 0. If you remember this formula, it's charge over 4 pi epsilon 0. Then we said that it's pm, the vector pm over, we've been constructing this formula throughout to the power 3. Okay, if you remember this formula, this is the direct formula of show electrostatic of the charge. When if you remember at the beginning, when we have a charge here and the point M and we want to know, and this is P. Okay, this is how we constructed the formula. Okay, so from this is what the charge is on the disk. So this charge to be dq, then this is the formula. Then now all we do now here is just the remplace. So what is dq? We're going to start with dq. What is dq? This is a method which we call calculate direct calculations, where you don't apply other theorems, you don't say theorem de Gauss, you don't say what, you just start calculating. You know that E is given by this formula. Okay, it's there in the book, you'll see it again. So dq is going to be equal to, now what is dq equal to? Okay, so as usual, this is a continuous distribution of charges here. So what are you going to say? You're going to say dq is equal to, and this is a surface, so you're going to say surface density multiplied by ds. Okay, always whenever you have a surface distribution of charges on a surface, you just look for your surface density sigma, you multiply by ds. So for you to find dq, so why there's dq, you replace it with the sigma ds. Oh, this is why we had to find ds at the beginning, because and this is how we find ds in cylindrical coordinate systems. You just multiply the parameters that are there, rho, d rho, d phi. I don't think it will be difficult for you to memorize this one. Okay, and then I just tried to show some people how this comes about, but anyways, it can be confusing to some people at the moment. Okay, or you can just search on Google how to find an elementary surface for cylindrical coordinate systems. This chop, mind you, we're just calculating the show electrostatic for this smaller portion, so we're going to weigh it elementary as well because it's for dq. And then so where there's s, we're going to put an expression of ds. So we're going to have sigma. Where there's s, we're going to put rho, d rho, then d phi. Let me even change the cooler. Okay. Then, so we're done with dq. dq is equal to this. So now we're going to find pm. So now, how do you find pm? Pm is very simple. Pm will be equal to po plus om. Actually, let me even go to this beautiful diagram. So, this is a smaller portion that we've chopped off. So we're going to first, to begin with, we're going to calculate for a smaller portion. Then for us to find the total E, we're just going to integrate. And when integrating on a surface, we're going to use the two integrals. So as you can see from this diagram, from this screen diagram, so we're going to assume, because our E is on the z-axis, so you're going to put at any point, let's say point M. So for you to find pm, you're going to, it's going to be po plus om. Okay, po plus om, which is given by, now in the cylindrical coordinate system, you always know that this radius is always called the rho. Okay, so it's going to be po op, this is po, so it's going to be negative, so it's going to be negative p, then this is the direction of rho, e rho, plus, then going up, you're going to have om, which is going to be, so if you don't know the magnitude, you just say z in the direction of z. So here they're using unit vector z. Now here, this component, you know that what you're calculating, your show electrostatic, is only in the z component, so you get rid of this component. you only consider this component when you're actually here they put it in the calculation, but they're going to get rid of this component. So you can just get rid of it here without even going further here. Okay. So for you to find PM, you just saw PO plus OM. PO is negative rho E rho, then this is the direction of E rho. M plus ZD K. Okay, let me even try to. So PO PM, because you have your PM in the location, so PM will be PO plus OM. Okay, now this is in the direction of rho, the radius rho. So you're going to say PM is equal to negative rho unit vector in the direction of rho. See the direction of rho, the radius. Rho is what represents the radius. Okay, then plus OM. OM, you don't know the magnitude, so just a Z in the direction of UZ. Then here you know that your DE. So if this PM has two components, you know that the component which has rho, you ignore it because we've established by symmetry that show electrostatic of a disk is only one variable dependent, which is Z. Okay, so for me on PM, I'm going to ignore this part, but PM is equal to this, but I'm going to ignore this part of PM. Okay, so here we're going to have dq. We said dq was sigma rho d rho d phi. Okay, then over 4 pi epsilon 0. Then what is PM? PM we found it to be, okay, I'll put it negative rho E rho. I can use this as a unit vector for E rho. Then plus Z Ez. Okay, over, how do you find, this is the magnitude to the power 3. How do you find the magnitude of the vector? So this is PM. How are you going to find the PM, the magnitude to begin with? The magnitude is simple. You just say the square root of P rho squared plus Z squared. Okay, now it's to the power 3, so we put this to the power 3. So this is going to be P squared plus Z squared, then to the power 3 over 2. Don't worry, this video is being recorded. You will go through it again. You have the day you'll be writing your exam, or the day before you'll be revising. So 3 over 2. So you just put here, this is calculate direct. You first find an expression of dq. For you to find the expression of dq, you need to know the surface density and what your dq is on the surface. This is ds. So dq was given by sigma surface density multiplied by the surface, which is ds. Now you know that the expression for ds is here. You just from plus and you put it here on dq. Then PM, you just find PM, as simple as that. Then PM is equal to this. Then the magnitude of PM to the power 3, magnitude of PM has given me to be P rho squared plus rho squared plus Z squared to the power 3 over 2. Okay, now you can decompose this into 2. As I said, I'm going to ignore this part. Okay, you can now multiply this multiplied by this part, this multiplied by this part. So this is what you're going to have. This is what you're going to have. You're going to have this part and you're going to have this part. So for me, I'm only going to focus on this part. If I do this calculation, this is what I'm from doing. So if I multiply this, multiply by this part, and this part, you're going to have this part. And if you multiply this, multiply by this part, you're going to have this part. But you know what? Your E is just in the direction of Z. So you ignore this part. You know what? Because the integral of this part will be 0. Oh, this part will be 0 somehow if you start calculating it. So instead of wasting time for you to start calculating it, you just say it's equal to 0 because you know what E, the component of that E has. So I'm only going to multiply this and this multiplied by this. Okay, so going back to our board. So we're going to multiply this and this multiplied by the part which has Z. So here we're going to have on a side together, on a DE. Mind you, we're calculating DE for now. Is in the direction on is only z dependent, is in the direction of z. So you're going to say sigma rho d rho d phi then over 4 pi epsilon 0 then multiplied by z ez over rho squared plus z squared to the power 3 over 2. So this answer that you're going to find is for an elementary part. So an elementary you found for an elementary part, this is going to be sigma rho d rho then d phi over 4 pi epsilon 0 then multiplied by z then over p squared plus z squared to power 3 over 2 then in the direction of ez. Now for you to find the total for the entire disk, you've only found the dE. So for the entire disk, you just integrate. You pass on the integral. Okay. So for you to find the total now, show electrostatic created by the disk, you pass on the integral. And when you are integrating on a surface, mind you, the disk is a surface. So you use two integrals. So we're going to integrate two integrals. Sigma rho d rho then d phi z over 4 pi epsilon 0 rho squared plus z squared to the power 3 over 2, of course in the direction of ez. Okay, now here notice that whenever integrating, you always integrate with respect to the rho, the phi, the dx, dz. So you only have two, you have the rho, you also have the phi. Okay, now rho is the radius. Rho is representing the radius. And you know that when you're integrating with respect to the rho is varying from 0 to r. Okay. Then phi is an angle that makes that moves in this direction, and phi moves from 0 to 2 pi. Okay. So here we're going to decompose this integral into two. Okay. Because we've got these two, d rho and d phi. So we're going to start with d phi. So phi, there's no phi component in here. So for the phi component, you can take it out. You can say you're integrating from 0. Phi varies from 0 to 2 pi. 2 pi is equivalent to 360. Okay, because the angle phi is changes from 0 to 360. It rotates around a full circle. Here, this is the angle phi. This is how it varies. Then the radius is rho 0 to r, the radius of the disk, the big R. So here you're going to say d phi. That's how you break down these two integrals. You then how to use the integrals. But for now, you say d phi, you get one integral with d phi, then with d rho, you're going to whatever is remaining. Because there's a rho in this component, so whatever is remaining will remain with rho. So phi, there's no phi in the integral. So here we're going to have rho. So we're going to have sigma d rho over 4 pi epsilon 0. Then we're going to have p squared over z squared, rho squared over 3 over 2. Okay. So then here you're integrating from 0 to r because you're integrating with respect to d rho. Okay, so rho varies from 0 to r. Okay, you get it. Then these are constants. Always, whenever integrating, you can take the constants out of the equation. We can't take this part because there's rho and you're integrating with respect to the rho, so you can't take it out. It's not a constant. So we cannot take the constant. And whenever this is like integrating with respect to, whenever you're integrating this from 0 to 2 pi, here the answer is just 2 pi. Okay, here the answer is always just 2 pi. Because here the integral of d phi is phi. Okay, then phi. So here the answer is going to be when you integrate here, you're going to have phi. Then from 2 pi 0, then we are going to say you're going to have 2 pi minus 0 according to the integral. What to do with the integrals? So here we're just going to have 2 pi. Okay. If you remember, when you're integrating here on a surface, it's just going to be s. So here phi is just going to be phi. Then you're going to put in the values from 0 to 2 pi. It's just going to be 2 pi. So in short, this part is going to simplify to 2 pi. 2 pi. And then now this part is why you're going to do your work. And then you can just take out anything that is constant, you take it out of the integral so that your calculations look nice. So here you're going to have sigma then over 4 pi epsilon 0. I think I've forgotten one variable here. I might have forgotten. I forgot z. Okay. Then even here we're integrating with 0, so even z can come out. I forgot z here. So z I can put it here. I forgot it. And then, which means this 2 pi and this 4 pi can cancel, but I'm not going to cancel for now. So here what you're going to remain with, and here the integral was 2 pi, you're going to have 0 r, you're going to have rho d rho. You just leave everything that is only having rho. So this 3 over 2. Okay. Now, to avoid confusing you further, what I'm going to do is I'm just going to give you the integral for this one. Okay. When you integrate this function, what you're going to have. Okay. If you want, you can memorize what it's going to give you, but you can. There's actually a way to understand like how you've arrived at that answer. Now it's going to be another whole other topic. Yeah, that's the only bad thing about this course is that there'll be concept of integrals that we'll do later on. So for now, you just there will be a point where you just have to like memorize what it will give you. Okay. So this integral, when you integrate, it's going to give us. This is what it's going to give us. So here we're going to say 2 pi over 4 pi epsilon 0 sigma z. Then here when you integrate, you're going to have, this is what you're going to have. So this is going to give you, so in integrals you put from 0 to r. So the answer is going to be, once you integrate this part, so the answer is going to be negative 1 over rho squared plus z squared, everything half. Okay. So so if you want to prove, you can try to integrate this with respect to rho within the question tree. It's going to give you this. So the integral of this function is this function. So for now, you can just memorize it for now. Okay, and it's not difficult. There are some similarities. Then here you can now put we will start with r. We can put r. So if you put, then this one I can simplify. Here we're going to have sigma z over 2 pi and epsilon 0. Then here I can put r. Okay, where there's rho, I'll put r. So mind you, the only place where we're going to put r is rho, because rho is the only one that varies from 0 to r. Okay, so here we're going to put t. So what we're going to have is negative 1 over, where is rho, I'm going to say r squared plus z squared to the power 1 over 2. Okay, then it's minus. So because there's a minus here, it's going to be plus. Then where there's a rho, you put 0 now. So we're going to have plus 1 yeah, over z squared to the power 1 over 2. Okay, this is what we're going to have once you evaluate your integral. So everything else here is just knowing that the integral of this is equivalent to this. Then you can put r in 0, and then here you start simplifying sigma z over 2 pi epsilon 0, and then here z squared to the power 1 over 2. So you can also simplify this. Okay, so I can multiply throughout by z. So I'm going to have, if I multiply z multiplied by this, I'm going to have negative z. So I'm going to say z multiplied by this, and here I can cancel this and this. So here, now once you cancel, if you had z squared, okay, z can either be positive or negative, the z squared will always give us the same answer. Negative z squared will give us z squared. Positive z squared will give us z squared. So whenever you had z squared somewhere, so to be safe, what we do is we always replace it with the absolute value of z. Okay. Okay, here you're going to have z. Let me not confuse you further. So z multiplied by 1, you're going to have z over, because of the z squared, we're going to put the absolute value of z because of the z squared for now. Then negative z, I'm multiplying by this z outside, over r squared plus z squared, the power 1 over 2. So this will be, no, I have to cancel out this z because I've already multiplied it throughout. Okay, so this will be the answer for the disk. So the show electrostatic, okay, the show electrostatic created by the disk will be sigma over 2 pi epsilon 0. Okay, then everything multiplied by z over its absolute value minus then z over r squared plus z squared, like that. Then in the direction of ez, or whatever unit vector, because not e is in the direction of ez, everything in the direction of ez. Okay, so that's how we calculate the show electrostatic creer pan disk using the method of direct calculations. So how many minutes am I remaining with? Okay, 20 minutes. That's a lot. So now here now, this is for a disk. Then we said at the beginning we said the disk is equivalent to, or the plan infini, I mean, the plan infini is equivalent to what? The disk with radius that approaches infinity, or radius equals to infinity in your terms. Okay, so now if I were to ask you to, they can ask you even in your schools to deduce on the deduce, that is from the answer you found. This is for a disk. So can you on the deduce the show electric creeper and plan infini? So after getting the show electrostatic creeper and disk, which is given by sigma over 2 epsilon 0, then z over absolute value of z. Whenever you are, this absolute value can confuse you. Whenever you had z squared, so you know that when you multiply this z squared multiplied by half, you're going to get z. So to be on the safe side, just put absolute value of z. Why? Because we said e is the z axis according to the symmetry, so it can be up or down. So if z was positive, this will just be 1. Z over z, this will just be 1. If z was negative, this will be negative z. So the absolute value to mean it will depend on the direction of z, but just put up absolute value of z for now. So minus z over r squared plus z squared as the answer, to the power 1 over 2. I forgot the 1 over 2, sorry. Here. Now the question is, if r is equals to infinity, okay, we're going to have this term is going to have, if r approaches infinity, so for a plan infini, so this is how you can kill two birds using one stone. You can calculate the show electrostatic by a disk. Then if they say calculate the plan for the plan infini, instead of doing the calculation and applying the theorem that goes that we did in the first session, you can just say the same answer for the disk. You just say a plan infini is visualized to be a disk with radius equals to infinity. This is where I apply this. So where is r, we put infinity. So in our equation, we're going to have sigma over 2 epsilon 0, if I'm not mistaken, E for a disk, then z over the absolute value of z, then minus z over r squared plus z squared 1 over 2. Okay, so now here we're going to put infinity. Absolute value z over, so infinity plus z squared. Now if you remember, if we're dividing by infinity, we always get 0. Okay, because z is constant here, so it's just for any variable that is constant. So over infinity, we always this part of the equation will be 0. Okay, if r is equal to infinity for a plan infinity, so we're going to have sigma over 2 epsilon 0. So this part will disappear. So we're going to have z over its absolute value. Okay, and this is just none other than, if z is positive, we're going to have sigma over 2 epsilon 0 z over z, which is 1. So we're going to have sigma over 2 epsilon 0 in the direction of k for the plan infinity. So if you remember, this is what we found. If z is negative, which means uh, here we're going to have z over absolute value of z is going to be z over negative z, which is equal to negative 1. So it's going to give us negative sigma over 2 epsilon 0 in the direction of k. So this formula has proved the formula for the plan infinity. So in conclusion, the show electrostatic created by and disk is given by sigma over 2 epsilon 0 z after a lot of calculations, of course, minus z over z squared, r squared plus z squared. Then for the plan infinity, so that is E plan infinity is equal to sigma over 2 epsilon 0. Then they are all in the direction of k. Okay, so and that is how you find the show electrostatic creer and disk, which has a lot of work. Then for the plan infinity, so for the plan infinity, we did it in the first session. So I've recorded both of these videos. So we have a disk. Okay, so what we do is, and we've established from symmetry, we've established that E is in the direction of, so E is in the direction of Z just. So it's on this axis. Okay, and this is the disk. So to begin with, what you do is, to be a bit fast, so this is the Z axis, this is the Y axis, and this is maybe the X axis. Okay, so to begin with, what you do is, you only get a smaller portion first, then you will just integrate it afterwards. So this is what we call an elementary surface ds. Okay, now this smaller portion will be parameterized in this way. This will be d rho. Then the radius of this circle is r. Then we're using this distance to be rho. Any distance from 0 to r will be rho. So this is rho. So this will be the smaller portion of rho, d rho. Then this is arc length. Then since this angle is phi, this angle will be, this smaller portion of phi will be d phi. This angle will be d phi. Then the arc length here is the radius, this multiplied by phi. As simple as that. So this arc length will be rho d phi. Then in order for you to find the surface or the area for the elementary surface, this information is to help you to say that the surface will be equal to d rho d phi. But they like to put it as rho d rho then d phi. You can, if you're failing to understand this, you can just memorize this always whenever we're finding the elementary surfaces. Some people use other notations, of course. This rho they can use a smaller r, so it's going to be r d, maybe theta, just depending on your school. But it's the same thing, as you can see, it's just a notation. But for now, we're going to stick to this notation. This phi can be theta. Okay, and then okay, for a smaller surface, it will have a smaller charge, an elementary charge. So, and we always have surface density sigma. So multiply sigma multiplied by the surface, because we are just first interested in this surface, which was ds. Then this ds will say sigma, we just find this to be rho d rho over d phi. Otherwise, if you just follow through, you find that it's very easy to solve. And then what else? So I find my dq. Now, let's say that our point M is here. Then this is maybe O. So this is already O. I can call this point where the charge is P. Now, for you to calculate the show electrostatic, we're going to use now the formula that we've been doing. Pm is a vector from the charge to M to where the point is. So show electrostatic, this definition is equal to the charge over 4 pi epsilon 0. Then you just say Pm over its magnitude, the power 3 cubed. If you remember this formula. For a non-parameterized situation, I've been emphasizing on this one. Now, you don't plus say this dq by this equation. So dq will be sigma rho d rho or d rho, then d phi over 4 pi epsilon 0. Then you just find p. Once you remember the formula, you just say, okay, dq is equal to this. Pm, what is Pm? Pm, if you remember, Pm, the coordinate systems, Pm will be equal to rho. Now, P will be equal to Po plus Om. So this will be equal to negative rho u rho plus Z uz. Now, since we already know that our E is in the direction of Z, so all other directions we ignore them. So the good thing is, in as much as Pm is equal to negative rho E rho plus Z Ez for K, this component you ignore it. Just say Pm is equal to Z Z. Pm is not equal to this, but because of our nature of show electrostatic, you just say it's equal to this. And then, so where there's Pm, you just focus on, you just say put Z. This is equivalent to, not equal to, Z Ez. Okay. Now, where there's Pm, you find the magnitude of Pm to the power 3. How do you find the magnitude of Pm? Don't forget Pm. So it's going to be rho squared plus Z squared, the root. Then the power 3 is going to be rho squared plus Z squared, the power 3 over 2. And then, so where is Pm to the power 3, you're going to put rho squared plus Z squared, 3 over 2. Then, since here you've found actually what you find is D, always the elementary show. Everything, because you're using an elementary surface. Now, for the entire disk, you just integrate your show. Okay, so for you to find the entire disk, you now integrate. Now, whenever you're integrating, you have two variables, d rho and d phi. So those two integrals, one will get d phi. Then we know that phi is varying from 0 to 2 pi. The other one will get d rho. Okay, then everything else that is not rho or phi, you get it out of the integral. So out of the integral, we have sigma over 4 pi epsilon 0. Then here we're going to remain with the rho d rho. Then even z is not these variables, over rho squared plus z squared over the power 3 over 2. Then this is rho is a radius from 0 to the actual radius. How many minutes am I remaining? 7. Okay. Then from here, I've not shown you how to integrate this one, or you can, if you know how to integrate, if you're clever enough and know how to integrate this one, you can do it. But from here, we know that the integral, this part will just give us 2 pi always. So here we're going to have sigma over 4 pi epsilon 0. Then this integral will give us 2 pi. Then here, the integral here will always give us negative 1 over rho squared plus z squared 1 over 2. Then so from 0 to r. Then you can now substitute in now how we do it with an integral. We say we put r. Now we only put r. R is rho is the only variable dependent on r. Rho is from 0 to r, so we put where there is rho. And we're integrating with respect to the rho, not z. So we put where there is r. So we're going to have sigma over 4 pi epsilon 0 2 pi. Then the first part will be negative 1 over r squared plus z squared 1 over 2. Then when you put 0 where there's rho, you're going to have Then minus, minus, so you're going to have plus, then you're going to have 1 over z squared to the power 1 over 2. Because you had z squared, you just put absolute value of z instead of saying z. So this can cancel. So if you put 0 here, at first you put r, you had this, then minus, okay. Then now there is a z here, I always forget it. There's a z on the constant. Then you can now multiply this z throughout. So you're going to have this 2 pi and this 4 pi will simplify. So you're going to have sigma over 2 epsilon 0. Then you're going to have z multiplied by this part. You're going to have z over absolute value of z minus, we put absolute value of z because it was z squared, okay? So it's negative z over r squared d plus z squared d, and there you have it squared. This is for a disk, okay? Now, for a plan fini, in case you've forgotten theorem de Gauss, you've forgotten the first station, but it's also important because I might ask you to use the theorem de Gauss. So it's going to be sigma over, the exam will be one of these. We won't just know which one is which. So we're going to have, for the plan fini, this is a situation where z is equal, r is equal to infinity. Now here we put infinite where there's r. This is going to be something over infinity. This is always 0. So just going to have this. So now this is equal to 1, but z, because it was z squared, z can either be negative or positive. So if z is negative, so if z is positive, z over z will be, so sigma over 2 epsilon 0. This will be 1 if z is positive. Then you just put in the direction of z because you know that E is always in the direction of z. Then if it's negative, just put, and this is what we found in the first session, if you remember, using theorem de Gauss. Okay,